We'll now look at complex numbers in Appendix A-7, the title of which is Complex Numbers, Quadratic Equations in the Complex Number System. So what we'll do is a basic introduction to the idea of complex numbers in this appendix. In section 4.6, back in the body of the notes in the main part of the book, there's a section related to complex zeros of polynomials, and there we'll state the fundamental theorem of algebra. So between this Appendix A7 and that section 4.6, together these make a pretty good standalone introduction to complex numbers and their interaction with polynomials. So the plan in this appendix is to define, add, subtract, multiply, and divide complex numbers, and we'll also solve quadratic equations using complex numbers. In the past, we've used the quadratic formula to solve quadratic equations and simply had either one real solution, two real solutions, or no real solutions in the event that the discriminant was positive, 0, or negative, respectively, I think. In this section, we'll further explore what happens when the discriminant is negative, and we'll actually end up in that case with two complex solutions. As you know, there's no real number x such that x squared equals -1. We now postulate the existence of a quote-unquote number, not a real number, satisfying the property that when multiplied by itself, it gives -1. It turns out this works, which is a bit of a surprise. It turns out this is a very mathematically fruitful thing to do. As I commented in section 4.6, we'll look at some implications for zeros of polynomials in a good deal more depth, still in the realm of Precalculus 1, but we'll see how the implication of taking the square root of -1, how that impacts zeros of polynomials in particular. And that's what the fundamental theorem is about. We have a senior level class called Complex Variables. Go to the link, the notes online, and there's a hyperlink to some notes for complex variables. And we've got graduate complex analysis classes too. So an entire branch of math deals with complex numbers. It's called complex analysis. So as a definition, or if you like a postulate, somewhat of an assumption, we say the imaginary unit, denoted with an I, is the number whose square is -1. That is, I squared equals -1. The number system that results from introducing this number I, along with the real numbers, is called the complex number system, denoted with a C. We denoted the real numbers with an R, we'll denote the complex numbers with a C. Stepping out of the pre-calculus realm here very briefly, it doesn't end there. Just as the real numbers are in some sense embedded in the complex number system, the complex number system is embedded in another thing called the quaternions. The quaternions lack certain desirable properties. Multiplication isn't commutative in general in the quaternions. As far as number systems go, the complex numbers are the best place to be. The real numbers are lacking something. They're lacking the ability to take square roots and negatives. The fundamental theorem of algebra is very clumsy when restricted to real numbers and very elegant when allowed to be done in the setting of the complex numbers. So in some sense, the real numbers, they don't have enough properties. The complex numbers, they got just the right number of properties. And if you continue on to the quaternions, they start to lose some properties. So the best place to do a lot of algebra, it turns out, in my opinion, is in the complex number system. My area is complex analysis, so I'm not entirely without bias on that, but things are neatest in the complex number setting. The quaternions are further embedded in something called the octonions, which are an even weaker still number system. There's a link to a PowerPoint presentation I have. I describe it as a deep mathematical adventure about the quaternions. It's fairly involved, but it's out there is the important observation I want to make at this stage. So back to the complex numbers. Complex numbers are numbers of the form a plus bi, where a and b are real numbers. The real number a is called the real part of this complex number, and the real number b is called the imaginary part of this complex number. So real and imaginary parts of complex numbers are themselves real. For complex numbers, there's kind of like a first expression and a second expression, the real part and the imaginary part. This is common notation. When we define some algebraic operations with complex numbers, we'll very much take advantage of this suggestive notation. I is the imaginary unit, so we must have algebraically that I squared equals -1. When a complex number is written in this form, a plus bi, or a and b are real, it's said to be in standard form. For definitions of equality of complex numbers, addition of complex numbers, subtraction of complex numbers, multiplication of complex numbers, curiously absent is a comment about division, but we'll take care of some division of complex numbers while we're at it. We have the following definitions. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. That is a plus bi equals c plus di, if and only if a equals c and b equals d, as stated, which makes perfect sense. Two complex numbers are added by forming the complex number whose real part is the sum of the real parts and whose imaginary part is the sum of the imaginary parts. So that's kind of a mouthful. This is where equations are useful. That is a plus bi plus c plus di. Add the real parts is a plus c. Here's the real part of the sum. And add the imaginary parts, b plus d I. These are definitions. You can't argue with them. They're very, very suggestive. The fact that they even have to be definitions might strike you as rather odd, but we're in an entirely new number system, so this stuff is necessary. Good news is it's just not very surprising. If you wish to subtract two complex numbers, we'll do a similar thing. A plus bi minus c plus di would be, if you like, dropping the parentheses, a plus bi minus c minus di. It's a definition. It looks like we've distributed. Distribution properties will hold. We'll collect together the real parts, the a and the negative c, to give us an a minus c for the real part of the difference. We got a bi minus di. Looks like we're factoring I out to the right-hand side and getting b minus d is the imaginary part of the difference. Technically, we're not factoring just yet. We're defining what these things mean. The product of two complex numbers, it is, by definition, a plus bi times c plus di. By definition is ac minus bd plus ad plus bc quantity times I. That's the definition, but that definition is inspired by requiring complex numbers to follow the FOIL process, which is really requiring some kind of distribution. So the definition of product that's given here, this is what kind of leads to distribution properties in the complex numbers. This piece of the definition is going to produce that. But if we were to FOIL this, then we'd have a times c, a times di, okay, that was a times the second entity, complex number, and then we'll take bi times c and bi times di. bi times c would give us bci, and bi times di would give us bd times I squared. So foiling produces this. I squared is by definition -1, so we get a -1 there. Here's a complex number. We'll just collect together the real parts, AC and minus BD, AC minus BD. That's where that minus sign came from. Ultimately, it came from I squared equals -1. And here we've got an AD and a BC, both times the imaginary unit I. So we'll write that as AD plus BC times that imaginary unit. The definition you can't argue with, but it's totally well inspired. It takes its inspiration from FOIL, first, outer, inner, last. So that's how we take products of complex numbers, and that gives us really the algebra of complex numbers. We haven't dealt with quotients, but we'll illustrate that with some examples. Speaking of, let's go to the supplements and look at a few examples. Perform the indicated operations, write the result in standard form, A plus BI. We've got a sum, a difference, and a product. So those three things we did define. Definition of complex number addition says if you want to add 4 plus 5i to -8 plus 2i, add the real parts together, 4 plus -8, being tedious with the parentheses and the negative signs and so forth. 5 and 2, add the imaginary parts together. That produces 4 minus 8 is -4, 5 plus 2 is 7, and it's multiplied by I. Easy enough. Subtraction, similarly easy. Only thing that could go wrong is dropping a negative sign. If we want 3 minus 4i minus the quantity, -3 minus 4i, we'll take the difference of the real parts, 3 minus -3. Be careful with the negative signs. And the difference of the imaginary parts, -4 minus -4, -4 minus -4i, the imaginary parts here. 3 minus -3 is 6, -4 minus -4 is 0. If you want, you could write this as 6 plus 0i, but it's standard just to not put the 0i term down and simply write this as 6. So it turns out this is a real number because the imaginary part isn't there. The imaginary part is 0. Products. Okay, we had a definition, but it's easier just to treat it with FOIL. That definition results from foiling. So if we want to multiply here, think of distributing the 5 across this. We'll have 5 times 2, 5 times -i, 5 times -i, then distribute the 3i. 3i times 2, 3i times 2, 3i times -i, 3i times -i. Simplify it a little bit. 5 times 2 is 10. This gives -5i, right? 6i, multiplying here. And 3, well, -3i squared. -3i squared. You know I squared is -1. That's how all this stuff started. And then we'll collect together real parts and imaginary parts. We've got 10 plus 3 produces 13 for the real part. -5i plus 6i leaves us with a plus 1i. And there's the standard form for the product. So there's those three as elementary examples. Let's return to the notes. Talk about conjugates of a complex number. So this is something fundamentally new. You've added and multiplied and subtracted real numbers before. This is something you don't do to real numbers, called conjugation, taking the conjugate of complex numbers z equals a plus bi. Quick comment, it's very common to use z to represent complex numbers. I don't know what the history is on that, but very common to use z to represent complex numbers, complex variables. In real settings that we've had, we'll represent functions as f of x, where x is some real number. In the complex setting, it's common to have f of z, where z is some complex variable. So we'll represent z equals a plus bi, some complex number. Its conjugate, denoted with a little overline, maybe read z bar, z conjugate would be a more appropriate way to read it, is defined as z conjugate. The conjugate of a plus bi is a minus bi. So to conjugate a complex number, you simply change the sign of its imaginary part and produce a new complex number, the conjugate of the original complex number. Straightforward. And there's a reason you would want to do that, and here comes the reason. Suppose z equals bi, a plus bi, then z conjugate is a minus bi. Let's look at the product, z times z conjugate. That would be a plus bi times a minus bi. We'll FOIL it again. And what you'll get is cancellation of some terms. You'll end up with a squared minus b squared I squared. Center term cancels, FOIL it out, you'll see that happen. Hey, the I squared is -1, so this will become a squared minus b squared times -1, or a squared plus b squared. So when you multiply a complex number by its conjugate, you get the real part squared plus the imaginary part squared. This sounds very Pythagoras' theorem style, except we don't have exactly a square on the other side of the equation. But the fact we got out the sum of two squares, very suggestive of something's going on here related to maybe the distance formula or the Pythagorean theorem, and there is. Notice ZZ conjugate then is a non-negative real number. Hey, a squared plus b squared could be 0 if a and b are both 0, otherwise it's positive. We only get 0 out when z is the 0 complex number, specifically 0 plus 0 I. Turns out this property can be used to define an absolute value on complex numbers. It's more commonly called modulus to distinguish it from absolute value. Some people use the term modulus and absolute value interchangeably. I prefer this different term in this different setting. But I got to roll with the punches. It is common also to call this the absolute value of a complex number. And that absolute value or modulus of z is defined to be the square root of z times z conjugate. So for this complex number, the modulus is the square root of a squared plus b squared. So there's how moduli are defined and computed. Some properties of moduli are the following. I'll actually prove one of these. Suppose we take the conjugate of a real number. That means you're going to change the sign of the imaginary part. For a real number, the imaginary part's 0, so nothing changes. -0 equals 0. So if we conjugate a real number, you simply get the real number out. That's why you didn't talk about conjugation until we got to the complex setting. The conjugate of a complex number is the complex number itself. That is, if we conjugate z in the parentheses and then conjugate that, we'll get the complex number z back. Yeah, because you will change the sign of the imaginary part, say from positive to negative, and then you'll change it a second time from negative back to positive, for example. So that's not in the least bit a surprise. The conjugate of the sum of two complex numbers equals the sum of the conjugates. That is, the conjugate of z plus w equals the conjugate of z plus the conjugate of w. If you think how you add complex numbers, you add them, I want to call it component-wise. You add the real parts and you add the imaginary parts. So that's not terribly surprising if you think how you add complex numbers. Adding complex numbers, pretty straightforward. Multiplying them's a little weirder because you got to deal with that FOIL stuff. The conjugate of the product of two complex numbers equals the product of the conjugates. The conjugate of z times w equals the conjugate of z times the conjugate of w. That's not surprising, but it's not immediately obvious. Let's go through proof of that. Okay, so we're going to prove this. It's not hard, it's tedious because multiplying complex numbers together is tedious. So take those two complex numbers, z and w, to be, say z equals a plus bi and w equals c plus di. Represent them in terms of their real and imaginary parts. Why would you do that? Because that tells me how to multiply them together. So we multiply in terms of real and imaginary parts. So let's take the conjugate of zw. First, we need to multiply z and w together. That's a plus bi times c plus di, and then conjugate. A plus bi times c plus di. Do your FOIL thing, produces this. Trust me on that. You're just distributing and doing FOIL, and it produces this quantity here. We get an I squared from this last term. So all we've done from here to here is collect the two i's together and drop some of the parentheses. This is exactly what we have in the previous statement. This I squared, of course, produces a -1. We'll have AC minus BD. Both of those are real. Bring those together, AC minus BD. We've got an AD times I and a BC times I. Okay, those AD and BC determine the imaginary part of the product. And we get AD plus BC, if you like, by factoring an I out from that. If you look back at the definition of product of complex numbers, it was exactly this when the complex numbers were of this form. All right, we drug this overline thing through the whole process of multiplication. So now we need to deal with it. It is conjugation. It means change the sign of the imaginary part. We have a plus sign in front of the imaginary part. We'll change it to a minus sign and drop the overline because the conjugation has been performed. So z times w conjugate is this quantity here. We're trying to show it equals z conjugate times w conjugate. In other words, this is the left-hand side of the equation. Let's show the right-hand side of the equation is the same thing. So let's compute z conjugate times w conjugate. Z is a plus bi. W is c plus di. We'll conjugate both of those. A plus bi. Here's a plus sign in front of the imaginary part. We'll change it to a minus sign. C plus di, plus sign in front of the imaginary part. We'll change it to a minus sign, producing this. Now we'll FOIL that because that's how you multiply complex numbers. A times C, A times negative DI, negative BI times C, negative BI times C, negative BI times negative DI, negative BI times negative DI, adding that, and we'll simplify. Two i's produce an I squared in this. Bring those negative signs out front and drop the parentheses, produces this quantity. Hey, the I squared produces a -1 again. And we'll have AC minus BD. We'll collect those two together. That's the real part. Here we've got negative ADI minus BCI. We'll factor an I out of this. Let's also factor a negative out. And let's rewrite this as negative AD plus BC. Parentheses around that, and then times I. So we factored an I out on the right-hand side and the negative sign out on the left-hand side to produce this. And that's the same thing we got before. So ZW conjugate equals this, and this equals Z conjugate W conjugate. So those two things are equal. In fact, there's what they both equal in terms of real and imaginary parts. So that establishes that the conjugate of the product is the product of the conjugates. It establishes this last little claim here. The others are pretty easy. That one's only a little bit more complicated because multiplication's complicated. Because multiplication of complex numbers requires that FOIL stuff. So it's no more complicated than FOIL and the weird little manipulation related to conjugation. So Z times Z conjugate, this is real. Turns out this is what we'll use when dealing with the division of complex numbers. If we want to find the reciprocal of a complex number, we'll use this conjugation stuff. If we want to divide complex numbers, we'll use this conjugation stuff. So we can put those reciprocals and those quotients in standard form for complex numbers. Here they want 13 divided by 5 minus 12i. We could bring the 13 out front and then consider this as 13 times 1 over this. So this is effectively dealing with the reciprocal of a complex number. Okay, so here's what we're going to do. We're going to make the denominator real, just as you would multiply a quotient with square roots in it by a certain quantity to make the denominator rational. In the setting of real numbers, you would rationalize the denominator. We're going to make the denominator real. Maybe you might call it, we're going to realize the denominator by multiplying by just the right thing. So we're going to take 13 over 5 minus 12i. We're going to multiply it by 1, but a special form of 1. We're going to multiply it by 5 plus 12i divided by 5 plus 12i. That's 1. Ooh, and 5 plus 12i, that's the conjugate of 5 minus 12i. So when we do the multiplication here, you know what's going to happen. This is a complex number times its conjugate. What do you get from that? You get the real part squared plus the imaginary part squared. Take a complex number times its conjugate, you get real part squared plus imaginary part squared. We said that in the notes, right? Let's look back real quick. Moving upstairs. Here it is. We took the complex number a plus bi, multiplied by its conjugate. We got a squared plus b squared. Right, a squared plus b squared. So the big observation, I guess, is that's real. It's not 0 unless z is 0. I worry about division by 0 still, but not a problem with what we're dealing with. But we get real part squared plus imaginary part squared when we process this kind of computation. Z times z conjugate, 5 squared plus 12 squared. That's 169, by the way. Hey, the denominator is real. So that's why we did that. 13 divides 169. That must be why they put it there. 13 times 169 is 13 squared, by the way. So anyhow, we can cancel this 13 with this 13 times 13, and we're just left with the 13 in the denominator. Now we've got 5 plus 12i over 13. They wanted this in standard form. That's 5 over 13 plus 12 over 13 times I. Couldn't put it in standard form unless we did this thing of making the denominator real. And you do that by multiplying by the conjugate of the denominator. In general, that's the way we'll deal with division. Let's look at a division question. Okay. Here's a quotient of two complex numbers. I don't think just long division is going to really get you anywhere. It doesn't really get you anywhere when you take a quotient of two real numbers. Then how about we do it the same way we did the previous one. Let's take 2 plus 3i over 1 minus I, multiply it by the right version of 1. What's the right version of 1? It'd be the conjugate of the denominator over itself. Denominator is 1 minus I. We'll multiply by 1 plus I over itself. Rewriting is given here. Hey, there's a complex number times its conjugate. 1 minus I, 1 plus I. Imaginary parts are -1 here and +1 here. They differ by a negative sign. That's conjugates. When you multiply such numbers together, you get the real part squared plus the imaginary part squared. We get 1 squared plus 1 squared. Or if you like, we get 1 squared plus -1 squared, if you view this as an imaginary part. The negative sign gets absorbed either way by the squaring. So we get a denominator of 2 in the numerator. I guess we'll have to FOIL that out. We didn't have to do this in the last one, but we'll do the FOIL thing. FOIL it out and simplify. We've done that many times. So pause the video, watch what's written, and convince yourself that it's true if necessary. But when you FOIL and simplify, you get -1 plus 5i in the numerator. We still got the real number 2 in the denominator. We'll split it up into real and imaginary parts, and there's that quotient in standard form. That's how you divide complex numbers. We didn't define that. We didn't have to. It was implied by the other ideas we had. It actually follows from the definition of multiplication and inspired by the idea of dealing with a complex conjugate. So there's how we take quotients. Okay. Here's an interesting observation. There's something special about the number I in the way it behaves when raised to powers. For one thing, when you square it, raise it to the second power, you know you get -1. Well, it turns out, just as if you'll take the number 1 or -1, raise them to powers, you know what they do. Raise 1 to powers, always 1. Raise -1 to powers, it jumps between 1 and -1. -1 to the first power is -1. -1 squared is +1. -1 cubed is -1. -1 to the fourth power is +1. It keeps bouncing between +1 and -1 as you raise it to positive integer powers. The number I, the complex number I, behaves in the same way, in that it bounces around. It bounces around between more than 2 values. It actually bounces around between 4 values. If we take I to the first power, we get I. You take I squared, you get -1. That's kind of how we define I. You take I cubed, we could write that as I squared times I. So there's a typo, I'm missing a little I. There should be an I, an additional I stuck over here. I cubed is I squared times I. Here it is down here. I will correct that. I squared is -1. So when we take I cubed and write all the parts down, we get -I out. 2 out of 3 of the i's produce a -1, and we have that third I left over to produce a -I. I to the fourth, well, that's I cubed times I, and we know what I cubed is now. That's -I. So we get -I times I. That's -I squared. I squared is -1. Negative times -1 produces 1 itself. So when you raise I to the first, second, third, and fourth power, you get out I, -1, -I, and 1. What happens when you raise I to the fifth power? Well, that's the same as raising it to the fourth power and then having an I left over, just like we did previously and should have done here. I to the fourth, I already know. We just saw that's 1. So we'll get 1 times I, and we get I back. It's going to repeat now. I to the sixth, well, how about that's I to the fourth times I squared. I to the fourth is 1. I squared is -1. We get -1 out, just like we did with I squared. I to the seventh, maybe write it as I to the fourth times I to the third. I to the fourth is 1. I cubed. I cubed was -1. Excuse me, I cubed was -I. So we get 1 times -I, and we get a -I out, just like we did with I cubed. I to the eighth is I to the fourth times I to the fourth. I to the fourth was 1, as we saw in the entry above. We get 1 times 1 is 1. It did it again. It went through the values I, -1, -I, 1. What happens next? If I look at I to the 9th, 10th, 11th, and 12th power, you'll get out I, -1, -I, and 1, respectively. It just cycles around, kind of like -1 cycles around, which just bumps back and forth between -1 and 1 when you raise it to powers. Well, I oscillates around. It takes on 4 different values, but only those 4 values when you raise it to powers. If we were to raise, here's the easiest one to see, if we were to raise I to some multiple of 4 power, well, I to the 4th is 1, you get a bunch of powers of 1, and you get 1 out. You raise it to, I want to view this over here, is 1 larger than a multiple of 4. Well, those multiples of 4 will produce 1, and then you'll have an I left over. You always get I in this column. 2 larger than a multiple of 4 will produce the same thing as I squared, because the multiple of 4 exponent simply produces a power of 1. You'll get -1 out again. 3 larger than a multiple of 4? Well, the multiple of 4 stuff produces a 1, leaving you with an I cubed, and that produces a -I. 4 larger than a multiple of 4 is a multiple of 4 again, and that's why we get the 1 out. And it did it again. I, -1, -I, and 1. So if we wanted to raise I to some big power, the fact that I oscillates around between these 4 values is going to be very useful, especially the fact that I to the 4th equals 1. Let's do some examples of that. Perform the indicated operation and write each expression in standard form. Okay, it's just a power of I, a negative power of I, and a sum of powers of I. Okay, I to the 14th. How about this? You add exponents when you multiply. That holds in the complex setting as well. So let's write 14 as 4 plus 4 plus 4. That's a 12. I need 2 more. So I'm taking 14 and peeling off 4s. 4 plus 4 plus 4 plus 4. 4 plus 4 plus 4, 3 times, plus 2 is 12 plus 2 is 14. But I to the 4th is 1, as we just saw. So we'll get a 1 out of this, and this, and this. So we'll have 1 times 1 times 1. I squared is -1. So we simply get -1 out. The multiples of 4 can be, in some sense, ignored. Strictly speaking, they're not ignored. They're 1. They generate a 1. Well, that doesn't change anything when you're taking products. How about I to the -23? Well, let's do the same thing. I to the 4th is 1. I to the 20th, that'd be I to the 4th times 5, or excuse me, I to the 4th to the 5th power. Multiplication of exponents in this setting, just like with real numbers. I to the 4th is 1, so that'll give you 1 to the 5th. It gives you 1 out. Whenever you have a multiple of 4 as the exponent, you're going to get 1 out. So if we look at I to the +23, I know that wasn't a question, but we look at I to the +23, we can write that as I to the 20th times I to the 3. We just saw I to the 20th is 1 because it's a multiple of 4. It's the same idea of what happened up here with I to the 12th. It's a multiple of 4, and so we get a 1 out. And then I cubed, we saw in the chart, was -I. So 1 times -I is -I, and there's what I to the 23 is. But they ask us about I to the -23. So we could view that as 1 over I to the 23. I to the 23 we just saw as -I. Let's multiply that by the conjugate of the denominator over itself. The denominator is purely imaginary. It's -I. Change that negative imaginary part to a positive part, giving us positive I plus 1I. So we'll multiply by I over I. Then we'll have I in the numerator. In the denominator, we get -I times I. That's -I squared. I squared is -1. -1 is +1, and we simply get I back out of that one. It all comes down to effectively ignoring multiples of 4 as the exponent. I look for the right words. So whenever you have an exponent that's a multiple of 4, you're going to get 1 out. If it's not a multiple of 4, I'd find a nearby multiple of 4 and then ignore that and deal with what remains. That's exactly what we did in number 36 here. So what you going to do with these? Well, I know what I is. I know what I cubed is. It was it's negative I. And did we just deal with that? Yeah, I cubed is negative I. I to the 5th, well, I'd treat that as I to the 4th times I. I to the 7th, probably treat that as I to the 4th times I cubed. And I know what I to the 4th is. I don't know what I cubed is. Reduce these exponents using this multiples of 4 idea. So let's do number 48. I to the 4th equals 1, basing it all on that. I guess there's probably other approaches. This is the approach that requires me to remember the least. So I do like that. It's not clunky in any way, but there might be a more efficient way. I to the 7th, yeah, let's write that as I to the 4th times I cubed. I to the 5th, yeah, let's write that as I to the 4th times I, and we'll leave these two powers of I alone. Add those exponents, and this is correct. I to the 4th is 1, so we're just left with I cubed. I to the 4th is 1. Here, we're just left with I, and we still have the I cubed and the I on the end. We got 2 I cubes and 2 I's, so let's combine those. You know what I cubed is? It's negative I. It's in the notes that we were talking about. So we've got 2 times negative I plus 2I. Actually, those cancel out and leave you with 0. So sum these, get 0 out. That's not immediately obvious unless you know how I behaves when you raise it to powers. Even then, it's not immediately obvious that the sum is 0. The little computation needs to be done. Back to the notes. And another topic dealing with square roots. When we introduce square roots of positive, well, non-negative real numbers, we dealt with the idea that there's 2 choices for, say, the square root of 9. We picked one of them, the positive one, square root of 9 is 3, and we call that, though really just in passing, we call that the principal square root of 9. Granted, -3 is a candidate for the square root of 9 as well, but the symbols square root of 9 means the positive square root. It's called a principal square root. We got the same problem here, except it's harder to deal with positive and negative when we got these imaginary numbers. They're not real, so they don't have a positiveness or a negativeness to them. Their real and imaginary parts do, but the numbers themselves need not. So for n, a positive real number, we define the principal square root of negative n, denoted square root of negative n, as the square root of n times I, where we've used the principal real square root and simply multiplied it by I, where I, of course, is the complex imaginary unit. You think you could find another candidate for a square root? Yeah, I bet if we took negative square root of n times I, if we square that, I bet you we also get negative n back. The negative sign would be absorbed in the squaring process. It means what it says. It's trickier in this setting. It's a little bit tricky in the real setting. You take a square root, you use the positive or the negative one. The symbols mean positive square root or non-negative square root, strictly speaking. Here, it means this. Is this positive or negative? That's not a meaningful question. It's an imaginary number, and they don't come positive or negative. Only real numbers come with a property of positive or negative. Imaginary numbers don't, and complex numbers don't. So I can't ask you if this is positive or negative. I could multiply it by -1 and produce a second imaginary number, but still, I can't talk about either of those as positive or negative. It is what it is. It's a purely imaginary number, neither positive nor negative. That definition comes with some slight difficulties. The complex valued principal square root function doesn't satisfy all the same properties of the real valued principal square root function. For example, if we were to take the square root of 100, you know the square root of 100 is 10. That's the meaning of these symbols. I'm also aware of the fact that if I square negative 10, I also get positive 100. But the meaning of the symbols, square root of 100, the principal square root, gives us 10 out. Put 100 in a calculator, hit the square root button, it'll tell you 10. It won't tell you plus or minus 10 because it's a function. It can only give you one value. So 10 equals the square root of 100. But we can also write 100 as negative 25 times negative 4. We would have been hesitant to do such a thing in the past because that looks like we run the risk of getting square roots of negatives. If we were to consider the square root of negative 25 times the square root of negative 4, notice I haven't said these are equal. I separated them verbally. I'm looking at something else here. Turns out this is different from that. That's the observation. If we were to consider the square root of negative 25 times the square root of 4, square root of negative 25, how was that defined? Take the square root of 25, really the absolute value of this, and then put an I out there. How do you take the square root of negative 4? Take the square root of 4 and insert an I. Take the square root of the positive part of this, take the absolute value, and then insert an I. Were we to do that, square root of 25 is 5, square root of 4 is 2, so we're left with 5i times 2i. Multiply those together, that gives you 10i squared. I squared is negative 1, so that gives you negative 10. So these two things are not equal because this thing equals 10 and this thing equals negative 10. So they're different. These two things are not equal. The square root of the product doesn't always equal the product of the square roots in the complex setting. And the fact they differ by negative sign is quite suggestive, right? We get 10 for one and negative 10 for the other. Yeah, I kind of suspect that negative sign comes out of the fact we're looking at square roots and having to choose a positive or negative square root. And something weird with this principal square root of the complex numbers. That square roots are defined in that way. The principal square root of a purely negative real number is defined exactly as we had it, but it leads to some new behaviors. We don't have the square root of the product as the product of the square roots. They're close, they differ by negative sign. Yeah, it's got something to do with the squaring function, I'm sure. But beware, we can take square roots of negatives if you'll let me use complex numbers, but that new square root function behaves in a bit more of an exotic way. The quadratic formula states, and we already done this, not with complex numbers. It says in the complex number system, the solutions of the quadratic equation ax squared plus bx plus c equals 0, where a, b, and c are real numbers. By the way, this works even if a, b, and c are complex numbers, but we're restricting our attention to real numbers here. We can still get complex numbers for solutions. Quadratic equation, real a, b, and c. The roots are given by the formula x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. Yeah, we did this before. Not exactly. This square root could involve the square root of a negative real number. And we've got that defined now. In the past, if you got a square root of a negative, you simply said no real solutions, which still holds, there aren't any real solutions, but it turns out there's complex solutions. What we get from the quadratic formula is ax squared plus bx plus c equals 0, where a, b, and c are real. A is not 0 because we get it in the denominator. Has two unequal real solutions if b squared minus 4ac is strictly positive, strictly greater than 0. Yeah, that's how you used it in the real setting. Has a repeated real solution, a double root, a root that counts twice in some sense, when b squared minus 4ac equals 0. But in these two cases, you took the square root of a positive real number, not a problem, or the square root of 0. Well, that's 0, not a problem. B squared minus 4ac less than 0, that's a problem if you restrict yourself to real numbers. Well, we're liberating ourselves from that restriction and considering complex numbers. In this case, the equation has two complex solutions, and neither of them are real. They both have imaginary parts. In fact, it turns out they're conjugates of each other. So the two solutions will come out as complex conjugates of each other in this event. So we ain't afraid of taking square roots of negative real numbers anymore. We have a way to do it using the principal square root of a negative real number. And let's illustrate that stuff with some examples. Solve this in the complex number system. X squared plus 4x plus 8 equals 0. Okay, we'll use the quadratic formula, which is valid if you'll let me use complex numbers, regardless of what happens. I'm not afraid of square roots and negatives if you'll let me use complex numbers. We'll use the quadratic formula involving the principal square root as we defined it above. X equals negative b plus or minus the square root of b squared minus 4ac over 2a. Here, a is 1, the coefficient of x squared, b is 4, the coefficient of x, and c is 8. 1, 4, and 8, the constant term, c. So we'll plug those numbers in. Let's see, b is 4, so we get a b here and here, here and here, keeping an eye on parentheses and negative signs and exponents and so forth. This minus 4 is part of the equation. Remember, when I substitute in like this, I put parentheses around the things we've plugged in. A is 1, so 1 goes there and there, there, and there. C is 8, C only appears here, and the 8 goes there. Let's see, 4 squared is 16. 4 times 8 is 32. It's subtracted. We get 16 minus 32 under the square root. In the past, I would have said, uh-oh, we got the square root of a negative. There are no real solutions. Well, that's true still. There are no real solutions. But this time, we get to talk about complex solutions. Let's see, out front, we just have negative 4. Denominator simplifies to 2. So we're good on that. 16 minus 32 is negative 16. We got the square root of a negative real number. It's okay. If you'll let me use complex numbers, the principal square root of negative 16 is I times the square root of 16. Square root of 16 is 4. So this quantity is 4i. So we get negative 4 plus or minus 4i divided by 2. 2 goes into negative 4, negative 2 times. 2 goes into plus or minus 4, plus or minus 2 times. So we've distributed there and simplified a little bit. And that's the two solutions. We were told we would get in the event that the discriminant b squared minus 4ac, in the event that it's strictly negative, strictly less than 0, we get two complex solutions. We were also told they'd be conjugates of each other. Here's the two complex solutions. Let's write them side by side without the plus or minus stuff. So we get negative 2 minus 2i and negative 2 plus 2i. And indeed, those two things are complex conjugates of each other. Their imaginary parts differ by a negative sign, and that's what conjugates do. As a set, the solution set as it's given here. So there's an illustration of solving a quadratic equation using the quadratic formula and complex numbers. Let's do another one. Okay, how about x cubed plus 27 equals 0? All right, that's a sum of two cubes. We're not really well equipped to deal with cubes. We did have a formula that told us a way to factor a sum of two cubes it was this formula right here. If we had x cubed plus a cubed, you can factor that into x plus a times this stuff. It's in section A3 when we talked about factoring in polynomials, where we mostly put emphasis on factoring quadratics and not factoring cubics, but we did have this formula listed at one point. So we'll take this as given and match up the pieces. X cubed plus 27, that equals x cubed plus a cubed, where a is 3. 3 cubed is 27, so we can plug a equals 3 in on the left-hand side of this equation, and that's how we'll factor this initially. So we'll have x plus 3 equals x squared minus 3x plus 3 squared. So that plugging a equals 3 in produces this as the factoring. A cubed is 27, as we said. So this matches this precisely when a equals 3. So we can factor it using the formula with a equals 3. Okay, so we wanted to set that equal to 0. If we do, then we're interested in when this factor is 0, and that occurs when x equals -3, and when this factor is 0. Can you find that? Yes. I got the quadratic formula. I can set any quadratic equation equal to 0, any expression of this form equal to 0, producing a quadratic equation. And I can find those places where that function is 0. It might require complex numbers. It depends on the discriminant, b squared minus 4ac. So the good news is you got any sort of quadratic formula, you can solve it. If you use complex numbers, not a problem. You can definitely solve it. You restrict yourself to real numbers. There might be conditions under which it doesn't have any solutions, but you know that. You know that from the quadratic formula. Quadratic formula tells you a lot of stuff. So first factor is 0 when x is -3. Second factor, we'll set it equal to 0 and see what x is, and that's what all these computations are. So quadratic formula gives us this. We have a is 1, the coefficient of x squared, b is -3, the coefficient of x, and c is 9, the constant term. Plug those 1s, -3s, and 9s in the appropriate place. That produces this. Be careful with the negative signs as always. Get a 3 out front, plus or minus the square root of -3 squared, that's 9. Minus 4 times 9, that's minus 36. Denominator is just 2. 9 minus 36, that's negative. Not a big deal these days, though. In fact, it's -27. So we get 3 plus or minus the square root of -27 over 2. Well, I can take the square root of -27 if you'll let me use complex numbers. Let's actually write that as 9 times -3. Square root of 9 is 3, so we'll pull that part out. And now we've got the square root of -3 part to deal with. To deal with that, you take the square root of the absolute value of this, that's the square root of 3, and you stick an I on there to deal with the negative part. So the square root of -3 is the square root of 3 times I. Same procedure that we did before. It's the principal square root of -3. Okay. Got a 2 in the denominator. Nothing simplifies this time. Write it as 3/2 plus or minus, another typo there, plus or minus 3 on the square root of 3 over 2 times I. So we get 2 solutions. Regrets on the typo. 3/2 plus or minus this quantity. So the solutions are -3. Don't forget the one that came from up here, the real one. 3/2 plus 3 on the square root of 3 over 2 times I, and 3/2 minus 3 on the square root of 3 over 2 times I, plus or minus. It's explicitly stated here. It's also in the solution set. And indeed, these two numbers are complex conjugates of each other. We knew that was going to happen when we set this equal to 0, provided we get the square root of a negative. Right? We've got the discriminant negative. All right, in that case, you get 2 complex solutions, and they're conjugates of each other. Their imaginary parts differ by a negative sign. It's that negative sign right there. Comes out of the plus or minus that should be here. So they're solving another system of equations. This one more complicated because it involved cubes. But we had a way to factor a sum of two cubes, and then it ultimately came to the question of addressing a quadratic equal to 0. And we're good at that. Square roots of positives or negatives. We're good at that now because we can use complex numbers in this section. Finally, without solving, determine the character of the solutions of this equation, x squared plus 6 plus 2x in the complex number system. By the character of the solutions, they mean that theorem that we stated about basically about the discriminant, the b squared minus 4ac stuff. First off, we need to write that a different way. So it is in the form of the quadratic equations we've addressed. A is 1, B is -2, C is 6 in the notation of the quadratic formula. So we simply took the 2x to the other side where it becomes negative. And then we'll consider the discriminant. And that's how we'll determine the character, as they say, of the solutions. Discriminant's b squared minus 4ac. B is -2, we'll plug that in here. A is 1, C is 6. Substituting those in the appropriate place. -2 squared is 4. -4 times 6 is -24. Simplify, we get -20. Of course, the important thing about -20 is it's less than 0. It's negative. Previously, we would have said no real solutions. Well, that's true if all you're going to do is talk about real solutions. But in this case, there's two complex solutions. In fact, the two solutions will be conjugates of each other, as we've observed in a theorem, and as we've seen in a couple of examples. When you deal with real coefficients in a quadratic set equal to 0, if you get complex solutions, they come in conjugate pairs, it turns out, for these. And that takes care of this appendix. So sequentially, next we'll go to the next appendix that we're covering, or alternatively, you might go into chapter 4 and deal with some of the complex stuff. These are likely supplements, and there's not time to deal with this complex number stuff in Precalculus 1, but I like it and it's good stuff. So there's an intro to complex numbers, and we'll see it in chapter 4, I think it's section 4.6. We'll see this encountered in the setting of zeros of polynomials. And you have to do this kind of thing here with the complex numbers to state the fundamental theorem of algebra, which talks about the number of roots of a polynomial equation. And it turns out it equals the degree of that polynomial if you count the right way and you use complex numbers. So have a nice day. I'll see you in the next topic, next episode. Bye-bye.